The youngest kids that I teach in school are just 10 years old. Can you imagine that some of them crack this colorful puzzle? It's true. The simplest and most beginner-friendly method relies on a layer-by-layer approach. Solving the first layer usually doesn't cause any trouble. There's plenty of flexibility to move the pieces around, so much so that we'll skip straight to the fun part. Tackling the second layer of the Rubik's Cube is where the fun starts to build. All you need is to apply one simple algorithm. Start by spotting an edge piece on the bottom layer that actually belongs to the second layer. Once you've found it, align it with its matching center piece. Here, for example, the green and red edge. Next, follow the easy step-by-step instruction and watch as the edge piece slides perfectly into its spot without disturbing the white layer you've already solved. This process is completely repeatable. Take the orange-blue edge next. This time the edge needs to move in the opposite direction, but no worries, the steps mirror the original instructions for a flawless result again. Sometimes you find that the second layer edge piece is in the wrong position. In this situation you can use the same algorithm to kick it out. Once that's done, locate the misplaced piece and guide it into its correct position. When 4 edge pieces are installed, the second layer is complete. A bit more energy is needed for the last layer and to complete the Rubik's Cube. In total there will be 4 short instructions. Let's first flip the cube upside down so that the finished white side is on the bottom. Then focus on the edges of the last layer. The first algorithm needs to be used once or twice until this nice yellow cross emerges on the top. Although all edge pieces are oriented correctly, they might sit in the wrong spot, as in our case the green and orange ones. The second instruction is designed to swap the front edge with the one on the left side. With the edges sorted out, it's finally time to deal with the corner pieces. Quite often, all of them are misplaced. Perform a quick sequence of 8 moves until at least one corner piece lands on its correct position. For example, in our case, the orange, yellow, blue corner is the first one that fits. Turn the cube so that this corner is at the front right and repeat the moves to cycle the remaining 3 corners until they are perfectly positioned. Finally, it's time to orient the corners. Each one can appear in 3 different ways, so you may need to repeat the flipping process once or twice for every twisted corner to align it correctly. Amazingly, while these transformations mess up the first 2 layers, don't panic, it's all part of the plan. Only rotate the upper layer to bring the next unaligned corner into the front right position. Watch in wonder as the Rubik's Cube seamlessly solves itself with the last flip of the final piece. Victory is yours. We can summarize all the performed transformations into one single word. Somewhat unintuitively, we read this word from right to left and from bottom to top, with each letter corresponding to a specific move. To track the moves consistently, we use the traditional Singmaster notation. For example, F as in front represents a clockwise turn of the face with the green centerpiece, while U prime as in up stands for a counterclockwise rotation of the face with the white centerpiece. At first glance, you might struggle to recognize repeated transformations shown by the arrows. This is because these letters always refer to the cube in its original unrotated state. When the cube is turned, the same arrow pattern is described by different letter combinations. You have just witnessed 131 moves to unscramble this magic cube. It can be done much better. What if I told you that you can solve every Rubik's Cube in less than 27 moves? This algorithm highlights an interesting limitation of human brains. Studies suggest we can only process 4 to 7 pieces of information at the same time. Luckily, the step-by-step algorithm always only focuses on a few pieces. And by solving the cube layer by layer, we can group the cubies of one layer into a big chunk so that we don't get mentally overloaded. With computational tools, we can transcend these mental limits and calculate the full state of the Rubik's Cube in one go. We can use mathematical operations to mimic the transformations, and there are ways to compute the solution to any scrambled cube. Our goal is to spotlight an algorithm that generates efficient solutions that work for any possible configuration of the magic cube. We cannot analyze the Rubik's Cube without borrowing a few ideas from group theory. As we discussed last time, the Rubik's Cube appears in overwhelmingly many 43 quintillion possible configurations. But even this amount of complexity becomes manageable when you can understand it as a product of many small entities. This will be our basic strategy. All ideas apply to a wide class of models, so-called permutation groups, so we can first play with the idea in a much smaller setup. For this, we will explore the symmetry group of a simple cube. Like in the case of the magic cube, we can describe its transformations with letters, and combinations of transformations turn into words. It's easy to apply a word and see the result. The opposite process is challenging. Given a particular Rubik's cube, what word or which sequence of transformations led to this state? Stabilizer chains are the mathematical tool that turns out to be helpful for this task. When we work with concrete examples, it's fairly easy to get a rough idea about the underlying concepts. Good names often give additional insight. In my opinion, stabilizer and orbit are great terms and can be understood effortlessly. Cosets and coset representatives might be a bit harder. If you are already familiar with these ideas, great. If not, our illustrated examples will provide an intuitive introduction. Even if you are not a fan of permutation puzzles, you are in for a colorful treat. So buckle up, ready, get, set, go. Consider all symmetry transformations of a basic cube. These are all the ways we can rotate or reflect a cube to return it to its identical form and position. We assume the faces, edges, and corners of the cube are indistinguishable, so any rotation that results in the same appearance is effectively the same cube. Here are some examples. Each one is presented as an animation, visually demonstrating how the cube moves from one state to the other. We label the corners of the cube. These labels help differentiate the otherwise indistinguishable parts of the cube and allow us to describe each transformation as a corner permutation. The first transformation is a 90-degree rotation. Its permutation can be described by two 4 cycles that move the corners. One is replaced by corner 5 is replaced by 7, and so on. The second transformation is a reflection across a horizontal plane. In this case, the permutation is described by 4 transpositions. Corner 1 is swapped with corner 5, 2 is swapped with 6, and so on. The third transformation is an inversion around the center of the cube. This is perhaps one of the less intuitive transformations. Here each corner swaps its position with the diagonally opposite corner through the cube's center. Once again, the permutation is described by 4 2 cycles. To even better see the action of these transformations, we also paint the faces of the cube with different colors. Easy so far, right? At this point, you might pause and think how many different images of the cube exist in total. There are more rotations and reflections left to consider. In fact, by combining these transformations, we can generate even more images of the cube. Also, for every transformation, there is an inverse transformation that undoes the rotations or reflections and restores the original cube. The smallest set of transformations from which all other transformations can be combined is called a generating set. There are many different choices for such a set, but since we've discussed reflection groups on this channel before, we'll use 3 reflections as the generators for the full symmetry group. We label them with the letters A, B, and C. A key property of reflections is that when the same reflection is applied twice, it brings the cube back to its original state. In other words, each generator is its own inverse. At this point, you might be wondering, how can we use only reflections to achieve rotations of the cube? Surprisingly, the answer lies in combining reflections. When 2 different reflections are applied in sequence, the result is equivalent to a rotation. Let's explore this idea further and bring the statement to life. We begin with the word AB. which means that a reflection of type B is followed by a reflection of type A. We can clearly see that it results in a 90-degree rotation of the cube. By applying this word 4 times, we return to the original state. Similarly, applying the word BC, the reflection of type C is followed by a reflection of type B, results in a 120-degree rotation. Therefore, repeating this word 3 times gives us back the original cube. We can formalize this fact by the identity BC cube is equal to 1. Finally, the word AC generates a 180-degree rotation. With the properties of these 3 reflections and rotations, we uncovered the formal definition of the Coxeter group B3. Looking up its properties, we find that it contains 48 different elements. So there should be 48 different images of our cube. Let's try to find them. A tree is an excellent tool to systematically explore all possible configurations of the cube. We begin with the cube in its original state. At the first level of the tree, we create 3 branches, each representing the action of one of the 3 reflection generators A, B, and C. From each of these 3 states, we now only apply generators that lead to new configurations. It wouldn't make sense applying the same generator again, since it would undo the previous transformation. To track these transformations, we collect the applied generators into a word. Each path of the tree corresponds to a unique word, and each word in the tree represents a symmetry transformation of the original cube. Although 48 different configurations are much less compared to the 43 quintillion different Rubik's cubes, it's still too many to verify at a glance. However, if you inspect the front faces of the cubes, you will notice that each color appears exactly 8 times. Focus on one of them, and with a slight rotation you can confirm that all 8 are distinct. Additionally, using corner labels, we can map each word to a permutation, as we will see shortly. An important observation is that the permutation label for each group element is unique, provided that the cycles always start with the smallest possible number. However, the words are not unique. You can always add combinations of letters corresponding to the identity without altering the underlying transformation. By design, the tree produces the shortest word for each group element. But as we will see later, finding the shortest word becomes challenging when not all elements of the group can be computed explicitly. Now let's take a moment to understand why some words, for instance CA and BC, do not appear in our group tree. We compare the 2 words AC and CA. Have a look at the transformations, and it becomes clear that both words lead to the same group element. This is straightforward to understand geometrically, since a 180-degree rotation achieves the same result regardless whether one rotates clockwise or counterclockwise. This fact can also be understood formally. It's fascinating how the abstract group relations can be used to manipulate words. We start with the identity AC squared is equal to 1. Now we apply C to both sides of the equation. The left side simplifies since C is a reflection that vanishes when repeated twice. A similar argument holds for the letter A, and we arrive at the conclusion without any doubt that AC yields the same result as CA. Similar steps can be performed to show that BC is equivalent to CB. Words are useful because they immediately describe the symmetry transformations that have been applied. For small groups, you can write down a complete group tree and simply look up a word for any given state. Unfortunately, this approach is not feasible for the Rubik's Cube. Its enormous number of configurations cannot be represented practically in a group tree. This is where permutations become essential. Let's examine them more closely. We begin by writing down the permutation for the reflection B. The first cycle indicates that 1 is replaced by 6 and 6 is replaced by 1. The second cycle is treated similarly. Observing the reflection, we see how the pairs of corners swap places. Next, let's apply a second reflection Z. Once again, the cycles tell us which numbers are swapped. When the reflection Z is performed on the cube, a serious issue arises. The corner labels on the cube do not align with the sequence of numbers in the permutation. In the numerical sequence, 1 is replaced by 6, and 6 is replaced by 4, and 4 is replaced by 1, forming the 3-cycle 164. Similarly, the rest of the transformation is described by another 3-cycle 358. However, on our physical cube, we observe that 1 is replaced by 4, 4 is replaced by 6, and 6 is replaced by 1. This discrepancy arises because permutations act on the labels of the corners, while symmetry transformations act on the position of the corners. The two perspectives do not directly align. Thankfully, there is a surprisingly simple solution to this problem. Perform the symmetry transformations in reverse order. For example, performing reflection C followed by reflection B matches the state described by the permutation BC. This method always works, and it's the reason why we read the words from right to left when describing such transformations. Let's apply the combined permutation of the rotation BC to the original permutation again. When the cycle contains more than two numbers, it indicates not a simple swap, but a cyclic exchange of numbers. The relation between permutations and symmetry transformations is helpful to keep in mind, but unless you aim to carry out such specific computations on your own, it's not essential. However, what comes next is crucial. We will demonstrate an alternative approach to systematically generate all 48 group elements without relying on the group tree. We begin by observing that the first corner can be replaced by any other corner of the cube. For example, the word BA replaces index 1 with index 2, and similarly the word ACB replaces index 1 with index 3. The set of all possible indices is referred to as the orbit of the first corner. When all possible corners are included in the orbit, the group is said to be transitive. Next, consider the 6 elements where the corner with the index 1 remains fixed and is not replaced at all. These 6 elements form a subgroup of the full symmetry group known as the stabilizer group of the first corner. In my opinion, the terms orbit and stabilizer are incredibly fitting here. They perfectly convey their meanings in this context. The elements in the first row are known as orbit representatives. This term is also well suited as different representatives could have been chosen. For each orbit point, there are exactly 6 distinct candidates. When we combine a representative with the stabilizer elements, we find all 6 possible representatives. But the most powerful insight is we can systematically generate all 48 group elements by composing each of the 8 orbit representatives with the 6 stabilizer elements. This organization of states is simpler and more structured compared to the group tree. For those familiar with group theory, this is a straightforward result. Any subgroup naturally partitions the full group into distinct cosets, as is demonstrated here for the stabilizer subgroup. Additionally, it provides a clear justification for why the total number of group elements is the product of the orbit length and the size of the stabilizer. Let's immediately apply our new understanding to the Rubik's Cube. What is the orbit of the first face? A corner face can only occupy a corner position, and likewise, an edge face can only replace another edge face. To make this distinction clear, we label corner faces with odd numbers and edge faces with even numbers. Apart from this restriction, the first corner face can be replaced by any other corner face. Consequently, all odd numbers between 1 and 48 appear in the orbit. For the first few orbit representatives, we explicitly demonstrate the transformation. From these configurations, we only need to retain information about the orbit position and the corresponding representative word. Through this process, we find that the orbit of the first phase index has a total length of 24. This in turn implies that the stabilizer group of the first phase must contain approximately 2 quintillion elements. If this were the end of the story, there would not be much to write home about. Luckily, we can repeat all what we've done so far in a second step with the stabilizer of the first phase. Let's return to our simpler example to understand exactly what this repetition signifies. To emphasize that the choice of indices is somewhat arbitrary, let's now examine the corner labeled by 6. The second element of this stabilizer does not alter this corner. The third and fourth element replace the sixth corner with corner 4, while the last two elements of the stabilizer replace corner 6 with corner 7. At this point, you can likely see where we are heading. The first two elements, epsilon and ABA, form the stabilizer of the stabilizer. The third and fifth element serve as orbit representatives. The fourth configuration can be expressed as a composition of BCB and ABA, which by chance also turns out to be the shortest word. Similarly, the sixth element of the stabilizer is composed of the third orbit representative and ABA. As a final step, the stabilizer subgroup of the stabilizer breaks down into two orbit representatives and a trivial stabilizer group. Thus, each of the 48 elements in the group can now be written as a composition of three orbit representatives. To compute the total order of the group using this chain of stabilizers, all we need to do is multiply the length of all the orbits. We now identify 11 distinct orbit representatives across 3 different orbits. The animation demonstrates how all 48 cube configurations are systematically composed, each one as a sequence of orbit representatives. Although reducing the group from 48 elements to just 11 representatives may seem like only a 75% reduction, the scaling to the Rubik's Cube group is extraordinary. With just a few hundred basic elements, we can systematically generate all 43 quintillion configurations. Let's explore how the chain of stabilizers further unfolds for the Rubik's Cube. We show a few examples of the second orbit in full detail to point out a few things that might not be obvious immediately. As you can see, for all final states, the phase with number 1 stays at its original position, as one would expect for the stabilizer group of phase number 1. While it is allowed to move during the transformation, it always returns to its original position. It's also plain to see why 9 and 35 cannot be part of the orbit. These phases are physically attached to the stabilized QB with the phase number 1. Therefore, they cannot appear in the orbit of the third phase. We skip ahead a few repetitions and look at the orbit of phase 12, when all white phases have been fixed. This time, we inspect the orbit for an edge phase. Since only one edge piece with 2 phases has been stabilized before, the orbit length is 22. For the first few representatives, we show the full transformation. For the remaining, only the final state is displayed. For this, as for any other of the orbits, we store the information of the orbit number together with the word of the transformation. Before concluding, let's take a closer look at the construction of the final orbit for the phase 32, which contains only 2 elements. Beside phase 46, no other phase can occupy the position of phase 32 without disturbing the previously stabilized phases. Interestingly, phase 32 and 46 belong to the same physical QB, meaning this transformation represents an edge flip. This edge flip is accompanied by the flip of a second edge piece. This observation reinforces the edge parity property introduced in the last video, which was key to determining the total number of Rubik's Cube configurations. Ultimately, this stabilized chain serves as the foundation for a deeper understanding of the magic behind the Rubik's Cube. The first secret that this stabilized chain unveils is the total number of possible configurations. Using first principles, we can now compute this number without relying on heuristic assumptions. The procedure is straightforward. Count the length of each orbit and multiply these values together. The result perfectly confirms the total of 43 quintillion configurations. Let's finally revisit the question of how the computer bot solved the Rubik's Cube at the beginning of the video in only 31 moves and explore how the stabilized chain proves helpful for this task. The procedure we are about to present is entirely generic and works for any configuration. Using the stabilized chain, we can derive a word, a set of instructions that brings us from the unscrambled cube to the desired state. Here's how it works. In our configuration, faces labeled with 1, 3, 4, 5, 7, 6, and 8 are already in their default position, so we can skip the first 7 entries of the stabilized chain. The first phase that requires attention is phase 13. In our target configuration, this phase is replaced by 41. This is where the magic of the stabilized chain comes in. By opening the box for the phase 41, we get a word that defines the required transformation. The phase labeled 13 is replaced by 41, and since this transformation is part of the stabilizer group, the other phases 1, 3, 4, 5, 6, 7, and 8 remain unchanged. Incidentally, this transformation also leaves the phase 2 in place, allowing us to skip yet another line of the stabilized chain and move on to the next phase labeled with 12. The same logic applies here. In the target configuration, the phase 12 needs to be replaced by 42. Opening the box for 42, we retrieve the appropriate representative, apply it, and move to the next line of the chain. Similarly, for the phase labeled 15, we retrieve the representative from the box 43 and we are done. Again, we can skip over phases 14 and 23 because these phases remain in their default positions. The orbit corresponding to phase 24 introduces an interesting nuance. Up until now, determining which box to open has been straightforward. However, this time it is vital to note that the stabilized chain references positions on the solved cube, not on the intermediate scrambled configuration. From the target, we know that phase 24 should be replaced by phase 12. While it might seem logical to open the box for phase 12, the stabilized chain maps positions based on the unscrambled cube. In the solved configuration, the current position of phase 12 corresponds to position 48. Therefore, we must retrieve a representative from box 48 to ensure phase 12 ends up exactly where it belongs. In principle, any representative within a box can be used, but some may provide shortcuts for later transformations. In our case, the next transformation brings the cube into the form of the target immediately, making a few more steps unnecessary. For this presentation, I tested a few representatives in each box to minimize the required number of steps. Finally, all representatives can be concatenated to form a complete word, the sequence of instructions for transforming the solved cube into the target configuration. Reading the word in reverse and swapping clockwise and counterclockwise rotations enables us to bring the target configuration back to the solved state. And that's it. This is the computational approach to solving the Rubik's Cube. You might now be wondering, where can you find the stabilized chain and its representatives? Clearly, performing these calculations manually would be extremely tedious. Fortunately, fast and efficient algorithms exist that can decompose any permutation group into such a stabilized chain. In the next video, we will explore one of these algorithms. The data for this video was generated using a small Java project. which efficiently computes the stabilizer chain for the Rubik's Cube in fractions of a second. An implementation in Python would likely be slower but could reach a broader audience. Let me know in the comments which option you would prefer. That's all for now. Thank you for watching and see you next time. Bye bye.